Welcome to the South Notts Amateur Radio Club Foundation Training Online, and today we're going to discuss propagation. We're going to go through radio waves, VHF and UHF, HF and the ionosphere. Radio waves. So radio waves travel in straight lines just like light. They can be reflected or refracted and diffracted as well. So reflected, just like light reflects off a mirror. Refracted means that they are the direction is changed, and diffracted similarly in a different way. The light's direction is being changed, but again it's straight lines and then effectively bouncing, if you like, off surfaces or around a sharp edge. Radio waves get weaker as they get further away from the transmitter, and this is because they disperse as distance moves on, same as a ripple in a pond disperses as it goes out in all directions. So at a certain distance it will be weaker than at a closer distance. The distance depends on a number of factors as well. So the antenna has a big say in how the signal goes. The frequency changes the properties of the distance it can travel. The power that's used obviously is a factor. And then we need to take into consideration obstructions such as buildings, and also the conditions, weather conditions, things like that. As you'll see from the diagram there, as the frequency increases, the wavelength becomes shorter, and as the frequency decreases, the wavelength becomes longer. And if you look at the red line there, when we talk about frequency, we're talking about how many up and down squiggles within an inch, let's say. On the left hand side you'll see there's only one wave within an inch. So that is a low frequency, meaning it's not going up and down many times, and it is a long wavelength, which is a measure of the length of that wave going up and down. At the other end you'll see it's high frequency, there's lots of undulations, and therefore the distance of each one, the length of each one, is short. So the two are opposites, frequency and wavelength. High frequency means short wavelength, and low frequency means long wavelength. VHF and UHF. The range of VHF and UHF is less than that of HF. Typically, VHF and UHF is limited to just beyond line of sight. The range decreases as the frequency increases. At VHF and UHF frequencies, radio waves get weaker when penetrating buildings. Glass, however, is more transparent to radio waves, so a signal will go further if it can go through glass than if it's hitting a wall of a building. Walls generally really weaken radio waves. Bear in mind as well, poor weather, things like snow, ice, heavy rain, can all attenuate or weaken your signals, particularly at UHF and above. So when you're talking extremely high frequencies, the weather does make a significant impact on it. VHF and UHF can be blocked by obstructions, hence antennas are normally located outdoors and very high up to give it a good overview of the area. Hills can also cause what are called radio shadows, and if you look at the diagram below, if you're transmitting from one vehicle and there's a hill or a mountain in the way, that will block radio waves from reaching the car on the right there, and that dead area where they receive no signals is called a radio shadow. Antenna's position, meaning height, is often more important than transmitting power. In fact, I would say is always generally more important than transmitting power. So think about location of your antenna more so than increasing the output of your radio. Better locations for antennas also improve the receive performance of your aerial, so it's a win-win. Height is more important than power. The range of VHF and UHF is dependent on the antenna height, as we mentioned. The antenna gain, bearing in mind we've discussed Yagis already, that can really make a fantastic performance increase. A clear path, so if you can get your aerial high enough that there's nothing in the way between you and the other station, that's ideal. Whereas low down, if it's got to work its way through in between buildings and trees, that's really going to cause problems. And the transmitting power is a factor, particularly if you've got obstacles in the way. Clearly the higher the power, the more it can punch its way through. However, you'll find that power is not a fix for things like that. Height is. So higher antennas are preferable to higher power, as they improve both transmit and receive performance. Outdoor antennas are preferable to indoor or loft antennas as well, for the same reasons. The range of VHF and UHF can be extended by some atmospheric conditions as well. With VHF and UHF, they pass through the ionosphere, but propagation can occur through the troposphere, which is the lowest level below the ionosphere. Looking at the diagram here, you'll see the ground itself, the Earth, the troposphere, which is the low-lying areas, and then the ionosphere sitting on top. Certain conditions mean that your signals can be held within the troposphere, bouncing through it up and down to a greater distance when those conditions happen. And these tend to be sporadic E and something called atmospheric ducting. And these duct the signal through the troposphere, travelling further than if they were shot out in a straight line and went off into space eventually. A bit more about the ionosphere. So these are layers of conductive gases between 70 and 400 kilometres above the Earth. There's almost always a question on this. What sort of distances does the ionosphere live within? And 70 to 400 kilometres is the answer, so please remember that. The ionosphere is ionised particles, and it's mainly caused by ultraviolet rays from the sun. So when the sun's shining on your side of the Earth, these become very energetic and work really well. And in the evening, when the Earth's facing the other way, your part of the Earth's facing the other way, the ionisation decreases and you get less of the bouncing effect. VHF and UHF signals pass straight through these layers and are generally unaffected by the ionosphere. HF signals are refracted, meaning bent or bounced, if you like, back to Earth. So they'll go up to the ionosphere or into the ionosphere, and when it hits a region that has the correct properties, it will then be bounced back down again, as shown in the diagram here. So with ionosphere and HF, the ionosphere refracts HF signals, allowing worldwide communications beyond line of sight, since the signal bounces back and forth, working its way all the way round to other places on the Earth that are not line of sight. Refraction, here's an example. This happens with light as well, which is also an electromagnetic wave, and the properties are very similar. You'll notice the straws going in at a certain position, and then because the light is refracted inside the water, it appears that it becomes disconnected from the top half and sticks out in a different position, and this is just a trick of the light being refracted. So this sort of thing, this bending of the light to a different angle, is what happens with radio waves in the ionosphere at HF frequencies. HF bands. HF bands are open, meaning supporting this skywave propagation, at different times of the day and of the year. Each HF band is affected differently depending on its frequency. The sun's activity has a big effect on the ionosphere, as we've discussed a moment ago, and contact around the world is done using multiple hops. So as the signal travels out and bounces, it might bounce several times between the ionosphere and the Earth to make its way round to other parts of the Earth. And there are apps you can get on the internet and for most phones. If you look at the inset picture at the top right there, it will give you an idea of what the conditions are like for this skywave propagation for each pair of bands there, 80 metres and 40 metres. During the day there it was poor, during the night it was fair, and so on. And this updates daily to give you an idea of what that particular day's performance will be. So in summary, VHF and UHF is generally good for just beyond line of sight. VHF and UHF height is more important than power, and this is easily tested and proven. HF signals travel around the world and they're refracted by the ionosphere, and the ionosphere is a layer of conductive gases between 70 and 400 kilometres above the Earth. These are all key questions you might be asked in the exam, so please commit them to memory. If you have any questions or you're not sure about something you would like further explanation, please contact your tutor and they'll be happy to go into more detail.